Hey everybody, great to see you again. Mr. Smith here. In today's slide deck, we're going to give you all the basics that you're going to need to handle the math of sound waves. The good news is you've already done a lot of this math. In our last slide deck where we talked about the math of mechanical waves, we even used this exact example. So the math number one, the first formula that we use when we talk about waves is just the first formula we ever talked about in physics, distance equals speed times time. And the idea with these questions was you could have a sound wave traveling straight to a wall, or you could have a sound wave ricocheting off of the wall and coming back, and you just needed to be appropriate about thinking about the distance. Was it 2 times the distance from the boy to the wall, or was it 1 time? And so I'm not even going to work through a question of that. If you have issues with it, definitely go look at that first slide deck or talk to me in class. What I did want to do is to show you an example that we are going to use in the lab to measure the speed of sound. So let's check it out. So here's the deal. The speed of sound is really fast, more than 700 miles an hour. So for us to be able to measure it in the lab, we're going to need to use some technology. And here's how it's going to work. We're going to take a computer and have that computer act right here as a timer. And once we start the timer, we're going to make a loud noise. And so in this graphic, it's showed as a bang. And what's going to happen is this first microphone is going to catch that bang before this second microphone will, because the first microphone's just a little bit closer. So in doing this experiment, what we're going to do is something pretty old school and pretty simple. We're interested in the change in time, or the difference in time, between the time at which the two microphones catch the sound. So delta t is always, as you remember, thing 2 minus thing 1, so time 2 minus time 1. And so what I'm going to do is take 0.20292 seconds, that's time 2, and subtract 0.2 with a lot of zeros after it, seconds, and what I get is 0.00292 seconds. Okay, so the deal is that's how long it takes the sound wave to get from microphone 1 to microphone 2. And now what we're going to do is, because this is just a straightaway distance example, distance equals speed times time, we can use that information to figure out the speed of sound. So check it out. We're going to go and get v equals distance over time. And we're going to do our best to carefully measure the distance between the microphones. So it's 1.00 meters, and divide it by that 0.00292 seconds. And what we're going to get in this example is around 342 meters per second. So that's right around the accepted value of 343. So when we do it in the lab, let's see how close we actually come out, okay? But that's an example of D equals VT. So the next equation is also one you've seen. Let's go take a look at that one. So the second equation that you'll remember is the wave equation. It's velocity equals wavelength times frequency. The math is straightforward. When you see hertz, you recognize that as a frequency. You see meters per second, you recognize that as a speed. And so we can just solve lambda equals velocity divided by f. Let's go get our answer, 343 meters per second over 40 hertz, which by the way is a pretty bassy sound. It's down near the low end of what people can hear, and that's why we've got a subwoofer that's making it. And the wavelength is really large. It's over around 8.6, 8.5, 8 meters or so. So it's a great big wavelength. Here's the thing. When you look at this twofold graph, you're really seeing what sound actually is. So we've got areas of compression right here, and what we just said is the distance between those for this wave is going to be around 8.6 meters. So the distance between compressions is 8.6 meters of the wavelength. So here is how it represents. That's an area of high pressure. So what's being graphed on this graph right here is pressure. And you can see that what goes on is pressure gets raised and pressure gets lowered. So in these areas right here where the speaker pulls back and creates a little bit of a vacuum, that's what we call a rarefaction, or an area of uncompression, okay? So that's the wave equation, and also a little bit more about how sound waves operate. So let's go check out the two actually new formulas that you're going to see in this unit right now. So here's the new formula. I'm going to give you the formula first, and then we'll say a word about how it works. New formula says this: intensity of sound equals power, so that's P, divided by 4 pi, and distance squared, where distance is the number of meters between the thing that's making the sound, so a loudspeaker, and where you're standing. So I'm going to work out the first example first, and then I'm going to want you to do one and see how it goes. And then we can compare notes. So I'm going to put in 1 watt for my power. 4 pi is just 4 pi. 1 meter is the distance in my first example, and squaring it doesn't really accomplish a whole heck of a lot. So I get 0.0796 watts per square meter. Okay, so what I want you to do is go ahead and set up the second example where your distance is 2 meters from the source and see how it goes. Okay, so here's my example. I plugged in 2 meters, squared it, and what I got was 0.0199 watts per square meter. So my intensity is always going to be measured in watts per square meter. I want you to notice something, and it backs up the graphic perfectly. Because circles get bigger as pi r squared, meaning the area covered by the circle gets bigger as pi r squared, the intensity of anything that comes from a central source, so it could be sound, or it could be light, or it could be food dye if you drop it in a big puddle of water, is going to get less, and it's going to get less really fast. So watch what happens. This number right here, 0.08 or so watts per square meter, is about 4 times the intensity of our second answer. And you can see it from the graphic. The surface area that's covered as we go from a distance of 1 to a distance of 2 gets bigger and bigger and bigger, and it's a geometric change, okay? So that's the intensity formula. It's one that we're going to use for sound. We'll use it for light. It's really an important one in physics. So let's go check out another example where we use this formula and do a little bit more with it. Okay, so here's the deal. So we've got same speaker, 1 watt of power. We see the intensity right here, and so they're asking us to figure how far do you have to go. Really just an algebra problem, right? So we know it involves intensity. I equals P over 4 pi d squared. And to solve this thing for distance, we just cross multiply the d squared, so it comes up here, divide both sides by the I, and what I end up with is d squared equals P over 4 pi times I, and then square rooting both sides will let us get that d is P over 4 pi times I, all inside the square root symbol. Okay, so what I'm going to do is, what I want you to do is pause the slide and go ahead and plug this in and see how it goes. And I'm going to do the same thing on my end, plug in the numbers and see how it comes out. Okay, so that's what I got. 2.82 meters is my distance. There's a couple things in this slide I really hope you ask about in class because I want to talk about them. So let's go ahead and check out the last example where we show you how decibels fit into all this. So if you ask people about sound, one of the things that almost everybody has some experience with is the idea of decibels. And they realize, folks do, that decibels and loudness are connected with each other. And it's true. Decibels and loudness are also connected with the idea of intensity in a way that I'm going to show you. It's a perfect connection, and there's a formula that relates the two of them. So the dB reading that you're going to register on a decibel meter is going to be equal to 10 times the log, so the logarithm, of your intensity, divided by 1 times 10 to the minus 12 watts per meter squared. So let's go and give it a whirl and see what it looks like. If I plug in 10 times the log of my intensity, 0.01 watts per meter squared, and divide it by 1 times 10 to the minus 12 watts per meter squared, what I end up with when I push all the right buttons is a 100 dB number, so 100 decibels. I'll show you on the next slide real quick exactly what the button pushing looks like, and let's go wrap it up. So just in case you needed the help, let's go check out how that works on the Casio. So 10 times the log, so I'm going to come up here just below my x squared button, and then I'm going to open up parentheses and type in my intensity, 0.01 divided by 1 times 10 to the negative 12, and close those parentheses, and it's as easy as that. I've got my 100 decibel number. So let's go and wrap this thing up. So the final question is an important concept one. 90 dB isn't as loud as 100 dB, but what's the difference between them? Is it just a little bit or is it a lot? Here's the thing to remember. Because the decibel scale is based on logarithms, every 10 dB is actually an increase of 10 times the amount of sound energy. So 100 dB carries a lot more energy, 10 times the amount of energy as 90 dB does. And so we'll talk about this in class. It all gets down to how the ear is an amazing, amazing thing. It can capture very, very soft sounds as well as ones that are billions of times louder without getting damaged. Absolutely an incredible thing. So anyway, that's it for now. Those are all the math things that you're going to need to be able to do all the stuff you're going to do in this unit. So have a great day. Bring your questions with you to class, and we'll see you real soon. Take care. Bye-bye.